anything you try to optimize, that's why cache attacks were possible. That's why we have speculation, right? Speculation is there for optimization, I mean, for speech performance. Turn it off when you don't need it, but it's too primitive, right? We don't think about.
Okay. Yes. Thanks. I also know that I'm standing between you and dinner, I think. So let's see. Maybe high bandwidth. How many people are students here? Okay, a good chunk. PhD students? Masters? Undergrad? High school? Okay, not yet. Okay, how many people are attending the winter school? Okay, there's some overlap, but not necessarily. Okay, so let's get started. Just go ahead, okay. Oh, good. Something is not working. How many people are Lucas students? Frank asked me to ask this question, so I wanted to know how. Okay, let's get started now. So I'm going to talk about memory-centric computing. I think Ingrid gave a very nice talk on hardware security issues. I'm going to touch a little bit on hardware security also, and then talk about near memory computing and in-memory computing. We're not going to cover all the slides. There are a lot of slides, but if you want to sleep, this is the summary of the talk. Basically, computing is a huge memory problem. People have argued that computing has an energy problem. That's absolutely true. But most of that energy is really spent on memory. And memory is really responsible for other types of wastes that we need to deal with. Performance waste, energy waste, robustness problems, monetary cost, and hardware real estate. And people are seeing that monetary cost a lot, especially today with the memory prices skyrocketing. How many people are experiencing that? If you're building any hardware, you'll see more and more of that. And I like that actually, personally, because I think this is putting memory at the right place where it's supposed to be, as opposed to being a servant to some processor. So that's going to be the mindset of this talk. And I'm going to give you some examples of all of this. And this problem is becoming worse with more data-intensive workloads. So don't expect the memory prices to go down soon unless we find some big solution. And I'm going to argue in this talk that we can solve this problem by designing memory-centric computing systems. I'm going to take a two-pronged approach in this talk. We're going to look at technology scaling issues at the bottom that are essentially plaguing all of our systems. And to solve these issues that cause robustness problems, security problems, and also scaling problems, I believe we need to take an approach where we're much more memory-centric, enable memory to autonomously manage itself, as opposed to being a slave to the processor. And then the second part of the talk, I'm going to look at the higher level a lot, which is looking at application and system scaling. And this is not going well either today. We're basically trying to scale the applications and systems, but this is coming at a huge hardware and sustainability and power and energy cost. And if you want to actually fundamentally change that, we really need to take a different approach to computing, which is enabling memory to do computation. I'm going to give you examples of both approaches. So let's get started. Computing today is bottlenecked by data. A lot of applications are data intensive. These applications require rapid and efficient processing of large amounts of data. And this is increasing. Basically, we can generate more data than we can process. And this is not, we want to perform more sophisticated analyses on data. And clearly, this is true for machine learning. A lot of people talk about it. Memory and compute requirements are growing exponentially. That's why people are trying very different architectures like wafer scale systems. I'm not going to talk about that today. But it's not only machine learning. There are many, many other areas like video or genomics where we can generate a lot of data. And these may actually become even bigger applications going into the future. And they incorporate machine learning also. The problem is data access is a major energy and performance bottleneck today. And unfortunately, we're wasting a lot of energy. Moving data consumes energy, and we're moving data a lot from where it's generated to the sensors, from sensors to the storage to main memory to on-chip memory to registers, and eventually, after it gets to registers, it can get processed. This is causing a lot of energy waste because we're not processing data where it is supposed to be. It is generated or stored. And this is also causing a lot of performance loss. And we usually understand and try to fix the performance loss problems by complicating our systems. When we actually realize the performance loss because you're moving data, that's a latency problem. And if you want to tolerate that latency, what we do today is we actually design very sophisticated processors with many, many levels of caching hierarchies, prefetching hierarchies, out-of-order execution hierarchies also in both software and hardware, and multi-threading. All of these actually increase the area cost and also system cost. And sometimes they work. Most of the time they don't work, especially for many applications. I'm going to give you some data related to that. When they don't work, they actually compound the energy waste. And also they cause sustainability issues because we're actually generating a lot of huge chips with lots of hardware. So we're in a vicious cycle where we're really wasting energy by moving data and also trying to tolerate it. The problem is we're very cluster-centric, and this comes at great system cost. I'll give you some examples right now relatively quickly. This is a single node processor drawn with my Xfig in 2008. It's still somewhat similar. Basically, what you see here is cores, red parts. Consider them accelerators also. Everything else is there to store and move data. Caches, interconnects, other caches, other interconnects, main memory, controllers, other interconnects, and storage. If you do the calculations, more than 95% of the hardware real estate of a single node is memory, storing and moving data. Memory and interconnect are interchangeable from my perspective, actually, because it's communication and also storage, and you can actually interchange both. Now, I'd like to take the hat of a 10-year-old kid when designing systems going forward, because if you want to fundamentally fix the energy problem, you really need to think that way, in my opinion. And if you throw this picture to a 10-year-old kid and say to him or her that I'm putting all of my resources, almost all of my resources to storing and moving data, should that be my bottleneck? And they would tell you that that shouldn't be your bottleneck. Unfortunately, it is. So maybe we're doing something wrong. That was hardware real estate. This is performance, not my data. This is Google's data. It's a beautiful paper that they published in ISCA 2015. According to them, all of their data center workloads. And if you look at this picture, most of the time the processor is waiting for data to come back from memory. It's doing what it's supposed to be doing only 10 to 20% of the time. Take that 10-year-old kid, ask the question. I designed the system. Its sole goal for performance to finish instructions. It's doing what it's supposed to be doing only 10 to 20% of the time. Am I doing a good job? The kid would be brutally honest with you and they will say, go do something else. Hopefully go design something else. But maybe do something else also, who knows? Okay, that's a joke. Okay, that was performance. Let's take a look at energy. Energy is much worse, basically. The numbers skyrocket here. This is data that I borrowed from Bill Daly. Numbers have changed over time, but the disparity remains. A complicated arithmetic operation is very cheap in terms of energy today. 20 picojoules for the 64-bit double precision arithmetic operation. And memory access at the time is 16 nanojoules. That's 800x difference. So the question becomes, does it make sense to move the data from the main memory, in this particular case, to the processor to do this relatively complicated arithmetic operation. Of course, it's not dogma, this is science, and it's an optimization problem, right? And you can do the calculations to understand how many times you need to reuse that data element, and you will come up with, actually Professor Wenmei Hu from Illinois has done a lot of those calculations. He presents them in his research when he gives talks, and it's thousands of times, basically. Many applications don't have that much reuse, and compilers designing compilers to get that level of reuse at the general purpose domain is very difficult. Okay, that was a complicated arithmetic operation. Today, we don't want complicated arithmetic operations because energy is a problem. We want cheaper arithmetic operations. People are trying to do things with 4 bits, 2 bits, 1 bit, ideal, less than 1 bit maybe. Now, if you actually do 32-bit operations on 32-bit data, 32-bit add, the disparity increases. That's 6400x difference between a memory access. A memory access is 6400x more energy consuming than a 32-bit addition. Now, we're not even talking about storage yet. If you talk about storage, multiply that by another 10x, so 64,000x. Now that 10-year-old kid is going crazy. You're moving data, and you want to actually save energy. You're really wasting 64,000x energy. Again, overcoming that with reuse is very difficult. Okay, we tried to do a lot of studies to understand the impact, system-level impact of data movement on performance and energy and robustness. I'm going to give you a couple of data points. It's a study that we did with Google in 2018, where we analyzed the popular workloads in mobile systems at the time. This is Chrome browser, TensorFlow inference, video encoding and decoding. And on average use cases, we found out that more than 60% of the total system energy is spent on data movement. This is average. Worst cases are much worse, actually. Now, if you accelerate computation, meaning specialize things, like we do in machine learning today, data movement becomes much worse. So this is another study that we did with Google on the edge TPU. We analyzed the edge neural networks that are used at Google at the time. This is before the LLMs. LLMs make things even worse, actually, as I will discuss maybe later. And we found out that more than 90% of the total system energy is spent on memory in large machine learning models that are used in the field. This is just to give you an example over here. At the time, LSTMs and transducers used at Google were the largest ML models in the edge. And you can see that most of the energy is spent on DRAM and the off-chip interconnect. Okay, hopefully I've given you a lot of data points. There's a lot more over here. Maybe we'll get to it later. But essentially, we have a fundamental problem, which is we're processing data far away from the data. And to solve this, of course, we can patch things, right? And I believe what we've been doing in industry and also a lot of research, which is good, we should be doing that also, to figure out ways of patching this problem. But we should also be fundamentally rethinking how we actually solve the problem so that we don't have this big of a problem to begin with. I think we will need to do that. To enable that, we need to compute where it really makes sense, where data resides, and look at ways of doing computation with minimal data movements. That's what I mean by memory-centric or data-centric systems. And there are many places we can do computation. Today, we're restricting ourselves to this SRAM-dominated chiplet, a very small fraction of it. And yet there's a bigger part of SRAM over here where you can do a lot of computation. And then there's DRAM, and then there's storage, and then there's sensors, and then there's interconnects. Why not do computation everywhere? Now, there are multiple models where you could do this computation. If this were a larger talk, I would probably talk about distributed computing, but I'm not going to talk about that. We are very used to an accelerator-based model. Why not actually use all of those components as potential accelerators? Then the question becomes, what kind of acceleration capability do you add to different components, and how do you orchestrate that computation? And there are many questions over here, clearly, that span across the stack. That's why it's an exciting area right now. I'm going to talk about a couple of these things in the rest of the talk. How do you design the memory and the controllers to do computation? How do you design the processors and communication units? How do you design the software and hardware interfaces to enable this? How do you design the software stack, system software, compilers, and languages to take advantage of this so that the masses can do this with relative ease? How do we rethink the algorithms so that we can match the computation capability that may be different in memory, or that may be designed differently, or that may have different trade-offs? And my favorite is over here, the theoretical foundations of computing. I'm not working on it. How many people here are computer science folks? Okay, how many people have taken a theory of computation or algorithmic complexity class? Okay, so good. If you've taken that class, you counted operations to actually quantify the complexity of an algorithm. And maybe it doesn't matter as much based on what I said, right? how many operations you do is not that important, maybe. Maybe you should really be thinking about data movement in addition to how many operations you do. And that theory of computation is not present, as far as I know, as far as I've talked with theory people. It's not my area, but I would encourage people to develop a much more data-centric theory of computation. Okay, I will also say that this is not a new idea. We're not talking about memory-centric computing is not a new idea. There are a lot of smart folks who have walked this earth that have written papers. These are the earliest papers that we could find in the 1960s. They called it logic in memory, processing in memory, logic in memory, essentially the same thing. And there's another one from Harold Stone, who has a beautiful textbook, which you may remember. What is different today? Basically, I think we have nowhere to escape today. Whenever you need to change the paradigm, applications, requirements, and also technology needs to pressure you. And I believe all of them are pressuring us today. At the technology side, which I will start with, we're pressured a lot. Technology scaling is not going very well. And by adding computation capability, we can do much better. At the application side, I've given a lot of data. System side, we basically are wasting a lot of things. And we can change that by minimizing data movement. And also requirement side, requirements have changed. Computing was about cost and performance for many years. And then energy came about. And then power came about. And then sustainability came about. Hopefully it will come about. If you want to really maximize all of those metrics, you really need to change the paradigm, in my opinion. Okay, so I think we need to defy business as usual. Asking what the 10-year-old kid would do would be useful, perhaps. Okay, let me jump into memory technology scaling. That's the first part of the talk. And we'll talk about how to take a memory-centric approach to this. We've been building a lot of infrastructure to understand problems that are happening with major memory technologies, especially DRAM and flash. I'm going to talk about DRAM. I'm going to ignore flash for now, but that's extremely important also. And this is an FPGA-based infrastructure, which we call DRAM vendor, where you can change the timing parameters in a soft memory controller and temperature and the voltage and figure out what's going on in memory. You can basically violate timing parameters, or you can not violate, and you can test a lot of things. This is the HPM version of it that we have developed. And this is our laboratory at ETH, which is one of a kind, actually. Other people are building similar things, and we'd be happy to help anybody who's building this. We can test a lot of memories. And these are examples of infrastructures. This is what we had at CMU in the past, where we did a lot of RowHammer experiments. How many people are familiar with RowHammer here? Okay, that's good. We have an opportunity to reach more people. Okay, we have open source these infrastructures. This is the older version, this is the newer version, and people are using it. And one of the things that we studied, we essentially study a lot of issues in DRAM. One of the things we study is RowHammer. I'm going to focus on that a little bit. I'm going to give you a couple more things. So RowHammer is the fact that you can induce bit flips in commodity DRAM chips without doing anything illegal, by completely accessing DRAM legally at a user level. You induce bit flips. It happens because cells are too small and cells are too close to each other. So I'm going to abstract away things a little bit. This is two-dimensional array of cells. If you want to access one bit, let's say, in DRAM, you apply high voltage to the word line. This is called activate in DRAM. If you want to access some other row, you apply a low voltage to that same word line, you pre-charge 0. Now, if you keep doing this repeatedly, activate, pre-charge, high voltage, low voltage, high voltage, low voltage, before the cells get refreshed, it turns out physically adjacent cells that are prone to read disturbance actually lose their charge, and they get corrupted. Basically, your 1 turns to 0 or 0 turns to 1, depending on what you stored over there. Now, this is not good because we're just accessing memory legally without the intention of changing anything, but things change. So we call this the hammer row, we call it the victim row, and we said that this should not be happening. And we showed that essentially today, all of the chips are vulnerable to this effect. And this is because cells are too small, too close to each other. If access to one cell is interfering with the data stored in other cells. It's called charge coupling, and multiple different device level mechanisms affect it. And we want to make those cells smaller and closer to each other so that we can store more data. This is one of the things that has enabled machine learning, for example, storing more data. Right? And we want to do more and more of that. Unfortunately, as you do that, this problem becomes worse. Meaning the number of activations to induce a bit flip has reduced by more than 100x over the course of a single decade. Okay, this is our original paper. I will not go into more detail, but I will say that this is also a hardware security problem. When we first wrote the paper, we said that we should maintain the property that an access to one memory address should not have unintended side effects on other addresses or the other data that's stored in memory. And we said that someone can hijack your computer if you actually allow this sort of failure mechanism. And the good folks from Google Project Zero showed that exactly. I will not go into that in detail, but I have the link over here if you're interested. And over the course of last 10 plus years, many folks in hardware security community showed that you can take over a system in different ways. You can read data that you do not have access to because you can induce these bit flips in commodity DRAM, in user level programs. You can break out of virtual machine sandboxes. You can corrupt important data, meaning you can actually render ML inference useless by changing the weights or by attacking the right bits in memory. And you can also steal secret data, like steal cryptographic keys that you don't, the private keys, and also ML model parameters that someone may consider important. There's a lot more I can talk about this. I'm not going to do that right now. And this is not the only issue. Recently, we've discovered another issue called row press. I'll very quickly give you the idea. The idea is in RowHammer, if you want to get the highest number of bit flips before row press, you keep accessing a row repeatedly at the highest possible rate allowed by the DRAM standard. If you want to get more bit flips and make the issue worse, in row press, you access a row and keep it open for some time. Keeping the row open actually induces interference to some rows that are close by. And this, it turns out, this is a completely different read disturbance effect that was not documented by anyone at the device community. This is actually fascinating to me because normally the way technology evolves is you come up with some materials, and then based on those materials, you understand the materials, you develop some theory of devices, and then after that you build logic, and then after that you build architectures and systems. Here we actually, at the system level, figure out that there's something wrong with the devices that have been in use for 60 years. That's fascinating to me. That's the beauty of this laboratory. Okay, so I'm not going to go into the details of row press, but all chips are vulnerable to this effect also. And in the worst case, only one activation can induce bit flips. Okay, so I can keep going on, and I will actually do that a little bit more. But how do we solve this problem? The solution to this problem is very difficult, and we've always argued that you need intelligence in memory, some computation capability in memory. If for those of you who may know flash memory is intelligent controllers. We have storage controllers that are actually very, very sophisticated today. They're actually quite sophisticated, almost as sophisticated as our processors today. For DRAM, I think we need something similar, maybe not as sophisticated to begin with. And we've argued this for many years, and I can give you a lot of other papers that talk about this, but the good news is industry is listening. And this is one paper from SK Hynix, 9 years after we wrote the RowHammer paper. SK Hynix published this paper in ISSCC, where they publicly, this is one of the major DRAM manufacturers, and there are only 3 major DRAM manufacturers in the world, SK Hynix, Samsung, and Micron. These folks basically publicly acknowledge the RowHammer problem, and the solution that they developed is very similar to what we've been proposing. In fact, this is one of the solutions that we said was not a good idea because it was expensive. And I still think that it's expensive, but it's a solution in the right direction, in the sense that it's putting intelligence inside the DRAM chip or memory control, in this case, the DRAM chip. The idea is to have an activation counter next to each row in DRAM. This activation counter internally gets incremented by the DRAM. And if the activation is, if the counter is greater than some number that's determined by the manufacturer internally, the DRAM chip internally takes an action to refresh the adjacent rows so that you don't get these bit flips. That's the highlight. Of course, there's some obscurity that's inside the standard and that's inside this chip that we don't know exactly how it operates. The good news is this actually got propagated to JEDEC, which is the standards body that actually sets the standards for DRAM chips. And all DRAM chips going forward will implement this. This is actually a very difficult thing to do. Changing DRAM a little bit is difficult. And some industry veterans have said that this is the biggest thing that has happened to DRAM in the last 20 to 30 years. An intelligent controller inside DRAM. We actually talked with DRAM manufacturers, like when we looked at a lot of RowHammer studies, and they were nice enough not to kick us out of the room when we wanted these intelligent controllers inside the DRAM. So it's very difficult, as you can see. Okay, so they didn't want to do it, but they had to do it. Okay, the question, of course, is our solutions good? You don't need to be a 10-year-old kid to figure out that this solution is probably not a good solution for the hypothesized problem that you're thinking of probably right now. And solutions are not necessarily good. So actually that intelligent controller needs to become more complex according to our studies. And we publish papers. I'm not going to talk about the details, but you need actually more complexity to actually make the solution truly safe and secure and also high performance. And once you do that, it turns out the solution may still be vulnerable to denial of service attacks. And then if you actually want to prevent that, you need that even more intelligent DRAM control. So that's a fascinating area. Okay, the question is, of course, can we do better? I believe we need to change the DRAM interface. I'm not going to talk about this actually, because we don't have a whole lot of time in this lecture. We have an hour or, okay, something like that. I'm going to skip this, but essentially, we need to, the key idea is we want to enable the DRAM chip to do things by itself. Today, DRAM chip cannot do anything by itself. Memory controller needs to tell the DRAM chip, like in my pocket right now, hopefully not exactly, but when I touch it right now, the memory controller is saying the DRAM chip refresh, 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 refresh. It's doing that every 7.8 microseconds. DRAM chip is so incapable that it cannot even refresh itself. I think that's very sad. I think we need to enable this chip to do things on its own without the memory, be an adult basically, without the memory controller saying something to it. And this idea we call self-managing DRAM can enable a lot of benefits, which I'm not going to talk about. But it turns out to be not so easily accepted idea. This paper was rejected 6 times. A lot of you are graduate students over here, so don't worry about it. If you get rejected, believe in your idea. Of course, take the good comments and improve. Yeah, and we acknowledge all of those. The question is, are there viewers asking the right questions? This is something that I cannot answer. What are some business impediments of this approach? And maybe people should not be required to answer. Anyway, I'm not going to go over this in detail. This was accepted after 3.5 years, after JEDEC implemented something somewhat similar. Not as aggressive as what we wanted, which I don't believe is aggressive. Okay, anyway. So I think defining business as usual is good, but I think we should not be shackled by standards and reviewers. These are actually 2 things that unfortunately affect scientific progress. I think our litmus test should be to efficiently advance scientific endeavor, because if you have to think about the business impediments of a particular idea every time and bulletproof it that way, there will be very little progress in the world. And that should not be the goal, because maybe an idea inspires another idea, which inspires another idea, which inspires another idea, which inspires another idea, and eventually, with that transitive function, something may get implemented. Okay, if you want more of this, you can watch my Micro 2025 keynote talk where I describe a lot of this thing. Okay, there's more to come basically. Basically, DRAM has been around for 60+ years. Bob Denard is the inventor of it. And there's still a whole lot we don't know about DRAM. So DRAM has changed, of course, right? Technology scaling has happened. That's why we've been working on it. Aging is something that worries me. We have some data on that. More recently, we discovered 3 major issues with our studies. One is variable read disturbance, which was not known before also. And this is the idea that this is the phenomenon that read disturbance threshold, meaning the number of activations in this bit flip varies unpredictably over time. Ataberk, who's sitting over there, is the one who discovered that. If you want to learn more about it, talk to him. Basically, the problem is, if this is the case, how do you actually decide the threshold to actually take an action, take a mitigating action to prevent these bit flips? Very difficult to do. You need an even more intelligent controller that tests DRAM online. So that does online testing to actually figure this out. More recently, we've also shown that a single row activation can actually flip bits across 3 DRAM subarrays. In RowHammer, you actually affect a couple of rows around you. Whereas with column disturb, there's a column level essentially interference that happens across 3 subarrays, which means more than 3,000 DRAM rows can be affected, and it can get bit flips. It's not as big of an issue yet, but it's a technology scaling problem, and this problem may become worse. Ismail, who's sitting over there, can talk about that also. And existing solutions cannot actually fix this. So you need to actually have an even more intelligent controllers to fix this particular problem. And I'm going to talk about processing in memory later, but there's an interaction between processing in memory and read disturbance, RowHammer, for example. So if you're actually doing processing using memory, as we will discuss, RowHammer makes things much worse. You get a lot more bit flips when you're doing processing using memory. And this problem needs to be solved also. Okay, you may say that DRAM is old technology. Why are you talking about this? There are emerging technologies. Unfortunately, they're not doing too well these days, but people should be working on them. Just because Intel stopped They're emerging technology development doesn't mean that academics should not be working on them. But the problem is these technologies all have problems. Some of them have even worse problems than DRAM, like endurance problems, and they need intelligent memory technology controllers from the get-go. And if they actually scale to the levels that we have scaled DRAM and flash into, who knows what other problems they will have. Okay, so that's why we keep building our lab and trying to discover new things. I'm going to skip these, but there are a lot of read disturbance papers that happen also. We're holding a tutorial on DRAM Bender if people are interested in learning about this and also developing it. And we're very happy to offer our help with these tools that we have developed. Okay, now let me jump into computation side, which is the higher level. We talked about the technology scaling. It requires intelligent memory and computation. By the way, JEDEC DRAM manufacturers are adding these metadata to each row. And people at the higher level have been asking for metadata added to pages in memory for various reasons, like information flow tracking, etc., tagging of memory. If you can actually add these bits to DRAM to prevent RowHammer, why not also add things to DRAM so that you can actually enable some other functions? That's one example of processing near memory. So these things are not that different from each other from my perspective. If you're adding computation to enable robustness, you can add computation for other things also, because that computation is actually a relatively general purpose. Okay, I'm going to talk about two different approaches to processing in memory. Unfortunately, the terminology here is a bit messed up. There's the nature of memory, nature of processing in memory. I'm going to talk about that. There's the location. Location can be anywhere, as we have seen. And there's a type of technology. This could be also SRAM, DRAM, flash, etc. Nature is, there are only two types of nature, in my opinion. I'm happy to stand corrected. If you have any ideas, let me know. But today we design logic and memory. We design them completely separately. There are very different flows for designing logic and memory. And sometimes fabrication technologies are also very different, like DRAM and CMOS logic, right? Now, processing near memory says design logic and memory as you're doing today, but put logic closer and closer and closer to memory. It could be inside the memory controller, it could be near the DRAM bank, it could be inside the row buffer, it could be next to each cell, but logic and memory are designed separately. Processing using memory, and this is the idea that people have developed in the 1960s. Processing using memory is fundamentally different. The idea is you have logic and memory, forget about logic. Take memory and look at memory as a computational device, meaning memory has some analog operational characteristics that enable it to do computation. And every memory technology has this. They all have different types of computation capability. This is fundamentally different, and this was really examined from 2010s with memristors and DRAM in our case. I'm going to talk a lot about DRAM, ignore memristors for now, although they're also very interesting. Memristors, for example, can do matrix vector multiplication based on their analog operational characteristics, but in DRAM, we're going to do bulk bitwise operations, for example. In the end, I think we need to combine both because they have different characteristics. Processing near memory, you can build a lot more complicated logic because we know how to do logic today. Processing using memory, the logic you build is going to be determined by the capability of the technology, operational capability. But you can potentially enhance it by changing the technology a little bit also. Okay, but processing using memory can be much more efficient because you're actually doing computation using the operational characteristics without moving data to some other logic. Okay, so processing near memory is easier, as you have guessed, and it's being done in industry, and I think there's more to do here. We worked a lot with the UpMem company, which was bought recently by Qualcomm, and there are other companies like Samsung, SK Hynix, Alibaba, and Micron that have added computation capability near memory for especially accelerating machine learning type of applications. UpMem had a general purpose processor next to each bank, a multi-threaded processor, which is programmable using a version of C++, and they have their compiler. Unfortunately, they're out of business right now, and who knows what Qualcomm is doing with their people and IP. But we have several UpMem machines that people are interested in looking at these real processing in memory machines and programming, developing software stack, which we have been doing. We'd be happy to help. Okay, there's also a lot of interesting things that are happening in the interconnect domain. CXL, for example, enables computational offloading to different types of devices, which I think is, again, a step in the right direction in industry. I think 3D stacking can enable a lot of things for near memory processing, because here you can put logic underneath memory at high bandwidth, low latency, and low energy. And with technology maturing in 3D stacking, you can put much better logic. when we first started doing research in this area, we assumed that technology will mature. The logic layer will be a true logic layer. At that time, it was not like that. But with HBM4, hopefully that logic layer will come, and it could be customizable. Let's see. And there are other true three-dimensional technologies that are under development, like TSVs become hybrid bonding, and maybe monolithic 3D will come also. So here you can accelerate different functions in the logic layer. And we've done research in this area that I'm not going to talk about, which is very interesting. I'll talk about accelerating ML inference very quickly. This is the work that we've done with Google that I mentioned earlier. We've looked at essentially edge neural networks that were used at Google. These are Google Pixel phones, for example. And we found a lot of variations in the characteristics of the different layers in these edge neural networks, in terms of arithmetic intensity, how many operations you do per byte fetched, and in terms of multiply and accumulate operations that you have. And the approach that people have been using was to design monolithic accelerators that try to cater to all types of layers. What we suggested in this work was to actually have a heterogeneous accelerator. A software runtime, it could be hardware also, decides what kind of layer should go to what kind of accelerator. And we have one accelerator that's processor-centric, like today, and we have two accelerators that are more data-centric, which is on the logic layer of stacked memory, essentially, 3D stacked memory. And there's a lot more detail in the paper on how to design these accelerators. But if you actually look at this, the complexity of the system is higher because you have multiple accelerators that are heterogeneous. But the benefits that you get is you're trying to match the type of layer. If the layer is compute intensive, it goes to a processor-centric accelerator. If the layer is memory intensive, it goes to data-centric accelerators. And of course, there needs to be some classification for this. Again, I'm going to skip this, but you get significant performance energy improvements with relatively little changes, without changing the programming model. You just have a layer of software that decides what should be executed where. And this is what we see. You get 3x energy consumption reduction and 3x performance improvement at the same time. And also the hardware real estate, the compute-centric accelerator that you design doesn't need to be as complicated anymore because your buffers can be much smaller because you don't need to deal with the memory-intensive portions or memory-intensive layers that you have in your neural networks. Okay, that's Mensa. The principles are actually similar. When you move to the LLM world, the principles are very similar. There are compute-centric parts of the code. There are data-centric parts of the code, memory-intensive part of the code. Figure out what to execute where and design a system that does it well. This is a paper that we presented as FLOS, where we showed that there are some fully connected layers in LLMs are extremely intensive, as everybody knows, and they should be executed on a TPU or GPU. But there are some fully connected layers that are quite memory intensive, not as compute intensive, but more compute intensive than other layers. This we showed that they're better to execute on near memory processors with a lot of computation capable next to each bank. And there are some other layers like attention layers that require huge capacity, very large main memory bandwidth, and not as much computation because they're not compute intensive. You can disaggregate them a little bit farther in an accelerator that's near memory that doesn't have a lot of computation capability. And we showed that you get significant speed up and energy efficiency improvements compared to best prior LLM inference system. You can do more. In this paper, we challenged the assumption that you need GPUs. It's a bit hard to do, but we have shown that by taking advantage of the CXL architecture and modifying the CXL device such that you do complicated operations in the CXL device, and you do the multiply and accumulate operations near memory inside the DRAM chip, and also by having communication primitives across these CXL devices so that you can communicate nicely, we show that you can actually get higher throughput and lower hardware costs than a GPU-based system. I believe there's more work that needs to be done in this area. I think it's fascinating to try to replace GPUs. Okay, there's more, and it's in our paper. This paper keeps increasing. It's almost 100 pages now, and it's due for an update. Probably it'll become 200 pages because there's a lot of work going on in this area. Okay, how much time do we have? None. Okay, 5 minutes? Okay. Okay, then I'm going to cover processing using memory very quickly. Maybe only one slide. Let's see. So processing using memory, as I said, is fundamentally different. You have the memory technology, and we're going to use the memory technology to do computation. We're not going to add logic, except for orchestrating or enabling that computation, but we're not going to add logic for computation itself. And we've shown, we're going to focus on DRAM. You can do all of these in flash and emerging memory technologies. And emerging memory technologies can do even more, like matrix vector multiplication. In DRAM, unfortunately, we cannot do that. If you figure out a way to change DRAM to actually do matrix vector multiplication, that would be a publishable result. So this is a challenge for some of you folks who may be very interested in this area. But basically, we can natively support a lot of operations: copying, initialization, all block bitwise operations, true random number generation, physical unclonable functions, and lookup tables at low cost. And the idea is to activate multiple rows, either in succession or concurrently. And doing this concurrently enables computation block bitwise operations. And the most fascinating part of this is probably you can do this even in commodity off-the-shelf DRAM chips by violating timing parameters. So DRAM chips are not designed for this purpose, but in our lab, we show that by violating the timing parameters, you can observe these functions: bitwise OR, bitwise AND, bitwise NOR, bitwise NAND, bitwise majority, of course, and bitwise NOT. All of these functions essentially existing DRAM chips can do, and copy function. Copy is the easiest, actually. You can do that with almost perfect reliability, and you get significant performance energy improvements. So I'm going to skip some of these things. Maybe I'll get to the computation. This is copying. You can see more of that. Let's talk about computation. So this is 3 DRAM cells. And if you concurrently activate these 3 cells, what happens is they share their charge concurrently with a reference bit line. And if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state. So that's a bitwise majority function implemented using charge sharing. There's no majority gate, logic gate. And bitwise AND and bitwise OR derives from the majority. Bitwise NOT is at the end of the sense amplifier. So you actually get bitwise NOT because there's already a sense amplifier with a cross-coupled inverter. So you have a functionally complete chip, actually, if you can do this. And we have proposed how to do this in simulation, and we've shown significant performance improvements in the past. Now, we generalized it, we made it more programmable. I'm going to skip these things to get to what I really want to present. You get actually, in simulation, you get significant performance improvements. And you can actually do even more, which is decide your algorithm, change your algorithm, change how you do addition based on the bit width and based on the computation capability you have, so that you can actually get even higher performance improvements. I have a story about this paper also, but I'm not going to talk about that. Okay, the real fascinating thing is existing DRAM chips are already quite capable. We've shown that you can do copying and true random number generation by violating timing parameters. This is a framework that Ataberk has developed again over there. You can actually run end-to-end applications, and this is a RISC-V processor inside the FPGA. And remember, the RISC-V processor is executing a page copy. The page copy gets offloaded to the memory controller that we changed in the FPGA, and the memory controller violates the timing parameters to copy one page to another page inside the DRAM subarray. The memory controller also generates random numbers by violating the read timing parameter and reading cells that randomly fail, because the memory controller figured out that those cells were random number generating cells. So you can actually execute rand functions as well as page copy functions inside the memory controller with this real system, and we get significant performance improvements in applications that do that. Okay, more recently, we've also shown that you can actually implement all of these functions. I'll give you the basic idea. You can copy one row into many other rows with almost perfect reliability. This is fascinating. You can actually almost off the shelf use this one. And maybe there's a startup idea over here. You can perform the NOT operation, and you can perform AND, NAND, OR, and NOR operations. I'm going to talk about the NAND, NOR, and NOR. Very quickly, this is circuit theory. If you look at the subarray on the top, we have A and B, 2 cells, 2 DRAM cells. There's a subarray on the bottom. This is the open bitline DRAM architecture. This is a sense amplifier. Now, if you had a primitive to concurrently activate all these 4 cells at the same time, the sense amplifier would compare the average voltage of A and B at the top to the average voltage of X and Y. That's essentially a function. By deciding what to put in X and Y, you can compute a function of A and B, or the other way around. So we call this a reference subarray. If you set the values to VDD and VDD over 2, and there are ways of doing that in DRAM, in the compute subarray, you would compute a function and you can decide for yourself. The only way in which the compute subarray would evaluate to VDD at the bottom is if the average value of X and Y is greater than 3 VDD over 4, and that is satisfied if X and Y are both VDD, assuming 3 levels, sorry. And you have the NAND function on the top. So you can do the exercise for OR and NOR. So this is how DRAM works. And if you actually, this is theory again, if you actually test this on real DRAM in the lab, you can do multi-row copy with almost perfect reliability. You can do these AND, NAND, OR, and NOR functions with reasonable reliability. It's not perfect, clearly, because there's a lot of variation and there are a lot of error sources. But you still get 94% success rate in some cases. And this is on a chip that's not designed for computation. Now imagine what you could do if you actually go and design this chip for computation. I think I'll leave it at that since we are out of time. Are we out of time? Okay, I will not continue. There are more slides, but I'm happy to talk about them. So we should be designing these chips for computation, because even if we don't design them for computation, they're already doing computation.
Are you ready? Yes.
Once you start violating these timing constraints, how reliable is that? And this is a complete outside of memory, but it's SDG versus this sounds almost sacrilegious, right?
It sounds what?
Almost
Sacrilegious.
sacrilegious.
Oh, not sacrilegious. It's blasphemous, I think. Yeah, but basically, that's not what we proposed. The reason why we violated these timing parameters was to show that even if you don't do anything to the DRAM chip, you get these functions. It's to demonstrate that the theory is correct and what we propose is sound. The way to do it would be to actually implement this multiple row activation primitive inside the DRAM chip and support it. Ideally as part of the standard, but standards take many years to change. So hopefully some people will do it and support it reliably. And there needs to be some research to support it reliably. So if you actually violate things, yes, you will always have some reliability problem. We're actually looking into that also, identifying causes of why this may happen. So there could be some methods or error correction also, if that's what you want to do. If you really want to use a DRAM chip today, if you understand what's going on, and if you actually do some error correction afterwards, you could potentially use some of these things, but it requires you to really understand what's going on. But ideally, this should be supported naturally as part of the standard.